Welcome to CO450 Computer Architectures. This is week 13. First of all, we have to do a little recap on even and odd parity checking from the previous weeks. So if we go to the exercise sheet to start with, we can do a little recap of some questions that relate to even and odd parity checking. So here we are in the exercise sheet. So we can see that the first thing is a recap on even and odd parity checking. So using an even parity bit check, check the following data transmissions by adding your own parity bit in the empty column and tick in the appropriate result. So let's check the first one. So we got 1, 2, 3, 4, 5, 6, 1 bits, which is an even number. So our parity check would be 0. So under even parity, this is correctly transmitted, no errors. So next one we have 1, 2, 3, 4, 5. So that's an odd number of 1 bit. So an even parity check would produce 1, which means that we have an error within that data. Next one we have 1, 1, 1. So we have 1, 2, 3, 4, 5, 6. So again we would have 0 as our parity even check. So that means that this is correctly transmitted. And then we have 1, 2, 3, 4 ones. So again, we have 0, and this is correctly transmitted under even parity. So odd parity checks then. So here we have 1, 2, 3. So this would, under even parity, that would give us 1, which using odd parity means that this is correctly transmitted, because there's 3 1 bits there. Here we have 1, 2, 3, 4 1 bits. So odd would give us, or using even parity would give us 0, which would mean we are an error detected within that using odd parity, because it shouldn't be even. Here we have 1, 2, 3, 4, 5, 6. So again, that would be under even parity. That would be 0, but as we're using odd parity, that means that there's an error. 1, 2, 3, 4, 5, and again, even we go to 1, that means that this is correctly transmitted. So if we come down now, 2-dimensional even parity scheme. So check the transmissions below with a 2-dimensional even parity scheme by adding your own parity bits to the rows and columns and ticking the appropriate result. If you do identify a single bit error, reference which bit has the error by entering its row and bit number. So let's check for parity. So we're using even parity checks here. We're looking for an even parity scheme. So let's have a look on the first row. So 2 1s there, so that's 0. 2 1s here, so 0. 1, 2, 3, 4, 5 1s here, so that would be a 1. So we've got an error somewhere in that row. And then 2 1s there, so that's okay. And then column wise, we've got 2 1s there. That's even, 2 1s, even, 2 1s, even. Single 1, so that would be a 1. So we've got an error in this column. So where they correspond, B2, R3 is what we're thinking at the moment, just to check the other columns. So 0, 2 1s, 0. Okay, and that would give us 1 there. So this bit is incorrect. So we've got an error here, R3, B2. So let's put that in. So R3, B2 is where we have an error. So yes, we detected an error and we've been able to correct it. Have a look at this one. So what have we got here? So we got 4 1s, so an even parity check would be 0. 3 1s in this one, so even parity goes 1 there, so there's an error somewhere in that one. 2 1s, so even 0. And then we have 4 1s, so 0. And then column wise, here we've only got 1, so 0 for that one, 0, 0, 0, and 0, and again 1 there. So our error this time is in column B5, bit 5, row 2. So R2 B5 is where our error is. R2 B5. Oops. And so again, yes, we've detected it, and yes, we can correct it. And then odd parity this time. So we're going to use an even parity check, but we are looking for odd parity scheme. So let's see what we've got here. So using even parity, but we're checking for odd. So we're looking for essentially where we have zeros. So there's a 1 on that first row using even parity check because there's 3 1s there. There's 4 1s here, so that's a 0. That's not right for an odd parity. 1 there, 1 there, 3 1s, so 1 there, 1 single 1, zeros, so there should be a 1 there. 0 there, so it should be 1 here, 1 here, and 1 here, and again yeah, it should be 1 there. So we've got an error, and where the zeros collide, so it's B3 or R2 B3. So oops, R2 B3. And again, we've got an error, and we've been able to detect it. And then on this one, so we've got 3 1s, so even parity check would give us 1. Here we've got 4 1s, so an even parity check would give us 0. 3 1s give us 1. 1, okay. 1, 0. 1, 1, 1. Oh, yes. 1. And again, so again here we have 0 in B4 lining up with R2 B4 R2. So B4, oh, maybe I should do row first. R2 B4, there we go. Oh, B4. So again, error detected and corrected. Okay, that's good. So just a little recap on parity checking, odd and even parity check, single bit checking, and then with the 2-dimensional scheme as well from previous week. So moving on now, for this week, we're introducing the Hamming code. So in 1950, Richard Hamming introduced the 7-4 code. It essentially encodes 4 bits of data, or 4 data bits, into 7 bits by adding 3 parity bits. So the Hamming code 7-4 can detect and correct single bit errors, but can only detect double bit errors. So this is another parity bit scheme which allows us to detect single errors and correct them, but effectively can only detect double bit errors. It can't correct them. So it uses a Venn diagram giving a graphical representation of a Hamming code of 4 data bits, which we label as D, and 3 parity bits, which I've labelled as P. So the diagram that we use for the Hamming code is a Venn type diagram, 3 circles intersecting, and it's the intersections or the sections of those circles that are created from the intersection of the 3 circles that we label accordingly. So if you look at this diagram here, you'll see that we have parity bits for the 3 circles. So you can see parity bit 1, parity bit 2, and parity bit 4. The reason it's parity bit 4 is position 4 within the binary number. So we don't have 4 parity bits, we have 3 parity bits, but it's at positions 1 and 2 and 4 within the binary number that's produced. The data bits are then D3, D5, D6, and D7. So bits 3, bit 5, and bit 6 and bit 7 within the bits that are produced are the data bits. And you can see that they are overlapped. Each data bit is overlapped by at least 2 parity checks. So parity, so for example, data bit 3 is checked by parity bit 1 and parity bit 2. Data bit 5 is checked by parity bit 1 and parity bit 4. Data bit 6 is checked by parities bit 4 and bit 2. Data bit 7 is checked by all 3 parities. So there's multiple parity bit checking going on for each data bit. So it's quite a robust system. And so each circle in the Venn diagram has an even parity, essentially. So the parity bits are worked out as even parity. And if we look at the parity bit check values, P1 and P2 and P4, with this example, so we've got data bits 1101, and we can see that parity bit 1 is set to 1, because if we look at data bits 3, 7, and 5, which are contained within parity bit 1, the circle, the green circle of parity bit 1, we would see it would need to be 1, because that would give it an even parity, because those bits are 1, 1, and so D3 is 1, D5 is 1, and D7, which is contained within parity bit 1, are all 1. So it's 3 ones, so we need a 1 for the parity bit to make it 4 ones, i.e. even. Parity bit 2 has been set to 0 because it contains bits 3, 6, and 7. So if we look at 3, 6, and 7, we can see that we have 1, 0, 1. So there's 2 1 bits, so it's already even, so the parity can be set to 0 as well. Parity bit 4 will also be set to 0 because it contains data bits 5, 6, and 7. And again, it's the same thing, so it's 1, 0, 1. And we already have 2 1s, so even with the parity bit being set to 0. So we set our parity bits based on the data bits that are contained within the circle that the parity bit alludes to. So green, I've got green, blue, and sort of orange there with parity 1, parity 2, and parity 4. So if we consider a message having 4 data bits, which is to be transmitted as 7-bit code word by adding the 3 error control bits. So the 3 bits to be added are 3 even parity bits, P bits as I'm labeling them here, where the parity of each is computed on different subsets of the message bits as shown in this table below. So the complete 7-bit code word contains 3 parity bits and our 4 data bits, but for individual parity bits, so parity bit 1 contains data bits 3, 5, and 7. Parity bit 2 contains 3, 6, and 7. And parity bit 4 contains data bits 5, 6, and 7. And it calculates even parity for each of those parity bits based on the combination of data bits within its check. So why those particular bits? Well, the 3 parity bits 1, 2, 4 are related to the data bits 3, 5, 6, and 7 as shown in our Venn diagram. So each overlapping circle corresponds to 1 parity bit and defines the 4 bits contributing to that parity computation. So for example, data bit 3 contributes to parity bits 1 and parity bit 2. So it can be observed that changing any one bit affects the 3 parity bits. Changing bit 7 affects all 3 parity bits, while an error in bit 6 affects only parity bits 2 and 4, and an error in the parity bit affects only that particular bit. The location of any single bit error is then determined directly upon checking the 3 parity circles. So if we're using the Hamming code, the data message of 1011 would be sent as the following code word. So 0110011. And we can see that laid out in the table below. So each of the parity bits has been created from the combination of the data bits to be transmitted. So parity bit 1 was set to 0 based on the data bits within it, 3, 5, and 7 being 1, 0, 1. So even parity would be 0 for the parity bit. Parity bit 2 has been set to 1 because its bits within its sphere is D3, 6, and 7, which were all 1, so we had to have 1 for the parity bit. And then parity bit 4 was set to 0 because its data bits were 5, 6, and 7, making 0, 1, 1. So we had an even number of parity bits, so we had to set parity to 0. So when these 7 bits are entered into the parity circles, it can be confirmed that the choice of these 3 parity bits ensures that the parity within each circle is set to even. And you can see that a little bit more clearly, I suppose, with the circles there. So if you take individual circles, the green circle, the blue circle, and the orange circle, you can see that we've set even parity with the bits that are inside it. So even number of 1 bits in each circle. And we can then check the parity of each circle by doing an even parity check. So we check those bits, 4 bits at a time, the even parity checks, and we come back with all zeros, indicating that this is correct. However, suppose the message 0110011 is sent and a single bit error occurs, such as the code word ends up being 0110111. So that's what's received at the end of it. So if we do our checks with that, we will find that we will get errors. So the error in bit 5 can be corrected by examining which of the 3 bits was affected by the bad bit. So what we actually get in the end is an output where for each parity check, so parity bit 1 produces an output of 1, which under even parity means it's not correct. Parity bit 2 actually works out as being correct, but parity bit 4 is not correct, so we get a 1. Now what's interesting about the Hamming code, and I think this is the bit that is a little bit amazing really, how it kind of works, but its beauty and simplicity of the checking system here. The 101 that is produced there as the output of those parity checks actually gives you the number of the bit which is incorrect. So you end up in this case with 101, and 101 converted to decimal equals 5. So 5 is the bit that was actually incorrect. And you'll find that if you can try this yourself, and it's a good idea to just quickly do that, you will find that if you change bits, so generate even parity and then flip one of your bits and then recalculate it. And what you will find is always the number that's produced in the 3 digits that comes out from the parity checking will always indicate as a binary number, which you convert back to decimal, will always indicate the number of the bit which is actually wrong. And again, this is quite an elegant little solution. So it actually gives you the number in the error check, which I think is quite exciting. The first time I did this, I remember being very amazed that it would give you the number in the binary there. So this is the beauty of this particular system. So again, we have a little exercise sheet for checking this, so we can do some little questions on this to see how that kind of works. So here we are in the exercise sheet for the Hamming code. So check the transitions below by completing the Hamming code diagram and table for each one and ticking the appropriate results. So if you do, identify a single bit error, reference which bit has the error by entering its bit number. Okay, so let's have a look here. So we've got binary here. So let's write that out in the table first of all. So so we got 0. That would be 0. Let's do this as I go along. Really, it's sometimes easier to do that. So that's 0. And then we've got all 1s, all the other bits there. Okay. And again, we could, I think it's going to be hard in Word to put that, so I'm just going to go with the table. Obviously, if you print this out and do it as a Word overlay, you could put things on there, but I'm just going to use the table, I think, and check each one now. So using even parity check, so that would be 0, that would be 0, and that would be 0 as well. So by checking these, we can see that we've got correctly transmitted. There's no errors in this particular one, so they all work out as even parity. So that one's fine. Let's check this next one. So the first bit is 1, second bit is going to be a 0, third bit is also 0, the fourth bit is 1, sorry, the fourth bit is also a 0, fifth bit is a 1, and the sixth bit is also a 1 there. Okay, so let's check parity. So here you can see that we've got 1, because we've got an odd number of 1 bits. So we're using even parity, don't forget. So there is an error here already. Next one is 0, and that one is also going to be a 1 there. So again, we've got error detected. Can it be corrected? Yes. And which bit is actually wrong? Well, again, it's data bit 5 again. So E5. Okay, so come down. So let's check this one. So the first bit is 1, second bit is 0, and then the third bit is 0s, fourth bit then is 1 in this case, and then we've got that's a 0, and that's a 1, and the final bit there is all 0. Okay, so let's do a quick check. So first one, 1, that's a 1, and that's a 0. So we can see there the error. We have an error in this one. So our error here is 110. So that's going to be data bit 3. So D3, we've got an error, and we can detect that error, and we can correct it. Okay, so next one, first bit 0, 1, and then 0, 1, 0. There we go. So let's do the checks. So that one's 0, 0, and 1 in that. So 0, 0, 1 gives us data bit. Actually gives us the parity bit 4. Parity bit 4 is in error here. So don't forget the parity bits could flip as well. It doesn't have to just be data bits, of course. So in this case, parity bit 4 is actually changed. So again, error and corrected. Okay, so return to the slides. So this moves on to the final part of in fact the final thing for the entire module. So we finish in week 13. This is our final set of content, and this is the final part of week 13's content. So grey code is where we end. So grey code is a form of binary that uses a different method of incrementing from one number to the next. So with grey code, only one bit changes state from one position to another. So this feature allows a system designer to perform some error checking, i.e. if more than one bit changes, the data then must be incorrect. So you read the grey code diagram from the vertical center line moving in an anti-clockwise direction from segment to segment. So grey code is showed as a diagram, it's diagrammatical representation, and you can see the example of the grey code that I have on this slide in the bottom right corner. So you take it from the center position, center line, and you go anti-clockwise, segment by segment, like segments of a cake really, as you work your way round. And the segments, as you move round, are read from the center, sort of moving out. So we have 0, 0, 0. So white is 0, and black is 1. So the first segment would be 0, 0, 0. It's all white. The second segment then would be 1, 0, 0, 0, 0, and the third segment would be 1, 1, 0, 0, and then we would go to 0, 1, 0, 0, and you can see that. So as we're moving in from the outside into the center is how we read it. So in from the center, moving into the center, moving from the outside in, and you can see it translates then to binary. Well, what looks like binary numbers, but these are grey code numbers, so they're different to the binary numbers. But only one segment changes as you count round in Gray's code. So this Gray's code that we have here is counting upwards, but it's not counting the same as you would see in a binary sequence. So you can write out grey code, but you need to then convert it to binary in order to turn it back into decimal number effectively. So grey code, the way this works is you write out the grey code, then you copy the leftmost digit under itself, add the copy digit to the next grey code digit, and move towards the right. So you start at the left and move towards the right. And remember to use binary addition. So it would be 0, 0 is 0, 0 and 1 is 1, 1 and 0 is 1, and 1 and 1 is 0. There would be a carry 1, obviously in binary addition. Just ignore any carries basically. So if you get 1 and 1, treat it as 0, forget about any carries. And you write the result of the addition underneath the next grey code digit, and you repeat from step 2 until you're basically complete. So again, we have a little exercise for allowing you to do this conversion. So it's a conversion of the grey code would be all I want you to understand from this. So grey's code is used in engineering. It's just a different kind of version of kind of a binary system. But like I say, the key thing about grey code is it only has one step positional change between digits. So as the numbers count up in Gray's code, only one position changes. Unlike binary, where you can get the position of 2 or more changes happen. So it's much more practicable in an engineering context. So let's go to the exercise sheet. So here we are on the exercise sheet for grey code to binary conversion. So convert the following grey code to binary, and then from binary to decimal. So the first one we've done. So the grey code was 0, 1, 0, 0, and we converted that to the binary by taking the leftmost digit, bringing it down, and then adding it to the next digit to the right hand side of the grey's code. So we brought 0 down, and then we added it to 0, 0, 0, and that produced 0, which we put underneath. So 0 and 1 is 1, 1 and 0 is 1. So we ended up with 1, 1, 1, 0, 0 in binary, which of course is 3. So if we do the next one, so our grey code that we've been given here is 1, 1, 1, 0. So the binary, so bring the 0 down, add it to the next one across. So 1 and 0 is 1. 1 and 1 is 0. And like I say, we forget about carry 1s. And 1 and 0 is 1. So we end up with 1, 0, 1, which is 5. And that's in the base 10. Decimal, so again, grey code. Let's roll that out. So 1, 0, 1, 1. So bring the 1 down, add it to the next one. 1 and 1 is 0. 0 and 0 is 0. 0 and 1 is 1. So that gives us so that's 9 in base 10. There we go. Oh, a couple more. Let's copy this one out. Grey code 0, 1, 1, 1. Bring the 1 down, add it to the next one. That's 0, carry the 1. That's 1, 1. So again, in binary, that would be 11. Oops. And then we have 1, 0, 0, 1. So bring the 1 down, add it to the next one. 0 and 1 is 1. 0 and 1 is 1. 1 and 1, 0. So that gives us 14. There we go. And then finally 0, 1, 1, 0. Bring the 0 down, add it to the 1. 1, 1 and 1, 0, 0. So that one's 8. Oh, sorry, 4. 4, there we go. Okay, so it's quite simple to convert grey code to binary, and then obviously binary to decimal back again. So that is actually the end of computer architectures. Thank you for taking the module. Hope it's been enjoyable. I hope there's been things that you've obviously learned from it, and material that we've covered that you found interesting. It is the foundation of computer science. So if you really enjoyed this module, then I would suggest more books on computer science are in something to look at and have a view on. Obviously, I've put something on the reading list for that. But it's really the heart of what computing is. What we've tried to demonstrate to you here is what goes on inside the computer and how it calculates and how it uses logic to function and perform the mathematics underneath it. There's a whole load more that we could have covered and put into this module, of course, but you have to draw a line somewhere. But hopefully this has given you a sort of foundational introduction to the world of computing, understanding more about what you're doing when you're using high-level programming languages and the applications and so on. What's really going on kind of behind the scenes inside the circuitry of the computer, inside the CPU. So hopefully you've got something from this, and I've done well on the TCAs and so on. So thank you very much.